A very good morning to our lecturers. And today, my name is Satya Rao, ethic number 192342. I'm from Group 1 from Plant Design. My group name is sss.co. And today in this video, we are going to make a presentation regarding our plant design project, which is the production of methanol from methane. So now my other teammates will introduce their name.
Hello, my name is Nur Atika binti Ismail and my metric number is 193160. Our objective is to produce approximately 200 million metric ton per month with purity of 80% of methanol from methane. To um, to produce 200 million metric ton per month with 80% purity of methanol from methane, our group using natural gas as a source of methane to produce methanol. Uh, in order to produce the amount of methanol that we want, we use natural gas as feed. This is due to the higher price of methane. So we want to cut the cost for the production. So we will use natural gas as our feed.
So now I'm going to talk about the process of this plant design. So as you can see in this slide, we can see there are 7 units that we use in order for the production of methanol. The 7 units are absorber, pre-reformer, ATR, autothermal reformer, a separator or cooler, methanol reactor, flash column, and also distillation column. Each of 7 units have their own functions, and each of the 7 units operate and perform at a different temperature and pressure. So in order for the feed to enter the inlet of each unit, we will have certain compressor and also heater, and this is just a basic process route. The detailed BFD block flow diagram will be described later in the Excel in a while. So the detailed process of each of the unit will be discussed later by all of us in the next show. Okay.
Okay, so for our design project, we have divided into several parts. So first, I will explain regarding the three first part, the three first unit, which is absorber, pre-reformer, and also ATR, which is autothermal reformer. We also put some compressor and valve to adjust the pressure. Also some uh, boiler and cooler to adjust the temperature. So let's take a look at the first unit, which is absorber. For absorber is a non-reactive unit which is help to remove the H2S. So for our energy balance, I put there are two streams, which is stream 1 and stream 2 that I will um, focus for the absorber. The stream 1 I have put the compressor. This compressor help to increase the pressure from 70 atm to 74 atm. So by using this energy equation, um, I'm calculating the work shaft and I have got the positive value for the work shaft. Then for the stream 2, I have put a compressor and also the boiler. So this is the compressor for the stream 2. It also helps to increase the pressure, which is from 1 atm to 74 atm. By using the same energy equation, I have calculated the work shaft and I have also obtained the work shaft in positive value. As for the boiler, I'll also put sorry, for the second stream, I also put the boiler to increase the temperature from 25 degrees Celsius to 43 degrees Celsius. So I'm using the reference, which is the inlet reference, the inlet as the reference, which is MDEA, and also H2O as the reference. So I'm calculating by using the CP, and I got the Q in positive, which is an endothermic reaction. As for the absorber, because it is an non-reactive unit, I did not calculate any of the energy balance because I have obtained the temperature and the pressure same as the unit. Then the second unit, which is a pre-reformer. Pre-reformer is one of the reactive unit. So I'm using a valve to reduce the pressure and also a boiler. For the valve, I have using a valve to reduce the pressure, which is from 74 atm to 20 atm. Next, for the boiler, I will use it to increase the temperature from 43 degrees Celsius to 450 degrees Celsius. So for the boiler, I'm using the reference, which is the inlet reference, which is the methane, ethane, water, steam, carbon dioxide, and also the nitrogen as the reference. So by using the CPDT, I obtain the Q in positive value. And as for the pre-reformer unit, it is an reactive unit. So I so I will explain. So I will explain the unit, which is pre-reformer. So for the pre-reformer, um, we are using heat of formation to calculate the energy value. So I'm using the reference, which is methane, ethane, steam, carbon dioxide, nitrogen, hydrogen, and also carbon monoxide at 25 degrees Celsius and 1 atm. By using heat of formation, I have obtained the value in negative value, which is it shows that it is an exothermic reaction. So for the third unit, which is autothermal reformer, I will there are also two stream, which is two inlet stream, which is stream 6 and also stream 7. So I'm using one valve and also two boiler to adjust the pressure and also the temperature. For stream 6, I have put one valve and also one boiler. So the valve help to reduce the pressure from 20 atm to 1 atm, and also the boiler help to increase the temperature from 497 degrees Celsius to 800 degrees Celsius. So for the boiler, I'm using the inlet of the boiler as the reference, which is methane, steam, carbon dioxide, hydrogen, nitrogen, and also carbon monoxide at 497 degrees Celsius and 1 atm. Thus, I'm obtaining the Q in positive value as is an endothermic reaction. For the stream 7, I'm using only one boiler, which is to help to increase the pressure from 500 degrees Celsius to 800 degrees Celsius. So I'm using the oxygen in the inlet as the reference, which is at 500 degrees Celsius and also 1 atm. I'm obtaining the Q in positive value, which show is an endothermic reaction. Same as previous unit, which is pre-reformer. ATR, which is autothermal reformer, is also an reactive unit. Thus, I'm using heat of formation to calculate its energy balance. So as for the reference, I'm using the reference for methane, steam, carbon dioxide, hydrogen, oxygen, nitrogen, and carbon monoxide at standard condition, which is 25 degrees Celsius and 1 atm. And the Q that I obtained is in positive value, which is show is an endothermic reaction.
Would explain about the pressure pattern and distillation column. So this is the
Hello, my name is Nor Ami Samsul Badunai. Okay, now I will explain later about separation and methanol reactor. For the energy balance, we use the cooler and the compressor for the separation before enter the separation, and then after out the separation, we use the compressor and the compressor to calculate the energy balance. So from the ATR, the temperature going in is 815 and going out for the separation is 217. So we must use the cooler to reduce the temperature. After that, we use the compressor to increase the pressure from 1 bar equal to 15 bar. Then after finish calculate the separation, then we calculate for the methanol reactor. For the methanol reactor, we use the P equal to 15 bar and T equal to 270. So the temperature that going out from the methanol reactor is 262. For the pressure is 300 bar. From 15 bar into to 300 bar, we must use compressor to increase the pressure. But for the temperature, we do not use any because the slightly change only in 18 different temperature. Okay, now I will proceed with the how to calculate the energy balance. Okay, first and foremost is cooler. For the separation, we use cooler and this compressor. So I will explain about the cooler first. For the cooler, we need to maintain the pressure at the 1 bar. I assume that 1 bar equal to 1 atm, so it is easy to calculation. Okay, for this method, I use the reverse state at the CH4, H2O, CO2, H2, O2, N2, CO2, and at 850 Celsius at 1 atm. So I can get this H in equal to 0. So I have to calculate only the 7H. So I use the normal calculation for energy balance is CP value. I take for the table B2. So this is how I calculate. Then okay, this is the value that I get for Q. Q equal to NH. So I get the negative value because of heat is released to surrounding. More than heat is required to operation. So the have okay. Now I will proceed with compressor. Okay. For the compressor, I maintain the temperature, but I want to change the pressure. So I use the normal energy equation, delta H plus delta kinetic plus delta potential equal to Q minus Ws. In this, I assume that kinetic potential and delta H equal to 0, so Q equal to Ws. Workshop. So this is the total density of all substance that I use. So then this delta P is temperature difference between outlet and inlet. So this is conversion of how I calculate the work shaft, then I get this. Okay, next I will proceed with compressor for methanol reactor. For this unit, I assume that neglect the change of temperature because the change of temperature is very small. I assume that 1 bar equal to 1 atm, density is kg per m3. I use the same method as before this. This is energy, the normal energy equation. Then I calculate the work shaft. I get the value for the work shaft. Okay, so this is for the methanol reactor. Okay, for the methanol reactor, I use the delta H formation for each of the substance I have. Okay, the calculation is easy. Just use like before this. Q equal to Q minus work shaft equal to delta H plus delta EK plus delta E. And assume that work shaft delta E and delta H equal to delta E equal to 0. So Q equal to delta H. But we use the heat of formation, so we get heat of formation is from the table B1. So we get the value. So in this, we calculate the CP value by using the the value in the CP in the table B2. So I get this value. Okay. Now I will proceed with the another my group member Satya.
BFD for flash separator. As you can see in this flow diagram, the inlet of flash separator is the product of methanol from methanol reactor unit. So as the both unit methanol reactor and also flash separator has a different pressure, so we need to put a compressor. So the function of compressor in this part is to increase the pressure from 300 bars to 392 bars. So now I will explain in detail regarding the flash separator unit. Okay, before moving on to flash separator, I'm going to explain about the compressor before the flash separator unit. So the function of compressor, as I've stated before, is to increase the pressure, and so the changes in the difference in pressure is actually 92 bars. So we are using this formula to calculate the energy balance. As we can see, the diameter is constant, and also the change in elevation is 0. So we can neglect the change in kinetic energy and also potential energy. So the heat release or in is equivalent to work shaft. So in order to calculate work shaft, this is the formula. So as we can see here, in this case, we took a methane density as for the calculation, and has it as the largest mole fraction here. So after the calculation, we got the Q value. It's this is the value. So as it is a positive value, we can clearly say that the heat is needed in this unit. So now let's move on to flash separator. So before moving to flash separator energy balance, I would like to talk about the flash separator function. So we can see here the inlet of the flash separator is a product of the methanol reactor, which is in a vapor phase. So the function of flash separator is actually to separate the unwanted gases. So we have a two stream, F3, which is also which is a vapor stream, and F2 is a liquid stream. So the liquid stream will be the inlet for the distillation column. So now we are in this case we change the temperature and pressure. We set the temperature and pressure in order for us to get desired product and mole fraction for our product here. So the temperature that we use in this case is 192 degrees Celsius, and the pressure we use is 392 bar. So we did the calculation for energy balance for this case. So we have calculated the energy balance. In this case, we use this formula. This is the formula we use. As we all know, the kinetic energy, potential energy, and also the work shaft is 0. So Q is equal to change in enthalpy. So in order for us to calculate change in enthalpy, we use the normal method, which is as this is a non-reactive process. So as we are not using the standard, we're using the standard pressure. There's a difference in pressure, so this is the formula we use to calculate the energy for changes in pressure. So this is for real gases and this is for vapor and liquid. So the final value for this is negative 270 million kilowatt. This indicates that heat is released in this process. So now let's move on to the next unit. Before moving on to distillation column, we put the PRV, which is pressure relief valve. The function is to reduce the pressure. So it reduces the pressure from 392 bar to 3 bar. As we consume, this is an ideal gases. The change in enthalpy is 0. So now let's move on to the last unit, which is distillation column. So in this case, we have mentioned before, the inlet of this, the feed for distillation column is the product of the flash separator, which is in a liquid phase. So in distillation column, we want the products to be in vapor, the final product to vapor, which is to be sold with other unwanted substances. So the F3 here is the vapor phase and F2 is the liquid phase. So as you can check here, both this is a liquid phase. So I like to continue from where I left just now. So as we have seen here, the component here are methanol, water, and also other substances. The other substances are the gases, soluble gases in liquid, which we have seen in the flash separator. So we assume in this case that all the other substances, all the soluble gases, will be in vapor phase later, which is will go to F3 stream. So in for this calculation, energy balance calculation, we have used the same formula here, and the formula used, we can clearly see that work shaft change in kinetic energy and change in potential energy is 0. So the final formula is Q is equal to the enthalpy change. So after calculating all the energy balance, the value that we got here is 37 million kilowatt. As the value is positive, we can say that heat is needed for this process. We have seen here. Now my other teammate will explain about the costing here.
Okay, I will continue with the costing part. Okay, from our block flow diagram, the inlet or the material that we need to produce a methanol that we want to sell is natural gas, MDA, and water. So for the total spending, we need the initial money to produce 80% of impurity, with 200 million metric ton. So for the methanol, we get the value for after we produce, we sell it, then this is the price that we got, the total profit we got. So okay, for profit, the money that we got back, production minus spend. Okay, for production we get this value 3801600000000, and minus 9156927623000000. Then this is the value that we got. The value that we do not get the positive value because the rate of production is too small, or the rate of we spend the money for electricity is higher because of some issue. Okay, now I will proceed as for the conclusion. In conclusion, in order to produce the amount of methanol that we want, we use 5 times 10 power of 8 of natural gas as the input or the feed. So after we calculate all the value, we do not manage to get the profit from selling methanol. This may be because there are many waste products that out from stream. The waste product we do not recycle back because they will going out just like that. So maybe that is the reason why we have many we do not get the positive value of profit. So we should recycle the waste product, also reduce the heat production in all units to get the positive profit. So that's all from our group. Thank you. See you next week. Bye, doctor.